Spectroscopy is a technique commonly used by organic chemists in order to explore the details of the structures of the molecules that we're interested in. UV spectroscopy is a form of spectroscopy that uses ultraviolet photons and even visible light photons to probe the details of molecular structure. We're going to begin this chapter discussing ultraviolet spectroscopy because it is simple and I think it establishes kind of the fundamental principles of spectroscopy without getting too bogged down in a lot of details. Before we dive into what spectroscopy can tell us about the molecular structure, let's back up a minute and try to recall what you should have learned already about the nature of photons. Planck's equation gives us a mathematical relationship between the energy of a photon and the frequency of the photon. So energy is equal to Planck's constant h times the frequency of the photon. Planck's constant is a constant and therefore doesn't change under conditions that we experience in a laboratory, but the energy and the frequency can change. So given an energy value, 4.973 times 10 to the negative 19th joules, we can manipulate Planck's equation and solve for the frequency. So I just divided both sides of the equation by Planck's constant, and I rearranged it to give us frequency is equal to energy divided by Planck's constant. Now I can plug in my value for energy, I can plug in my value for Planck's constant, and divide them and end up with my frequency. If we pause a minute to think about the units of this particular chemical reaction, joules are on top and joules times seconds are on bottom. So joules are going to cancel out and the units of frequency end up being 1 over second, or seconds to the negative 1, or the term that I like is Hertz, just because it's easier to type. And all three of those things mean exactly the same thing. So Hertz was the last name of a scientist, and that was tacked on as a shorthand way of writing 1 over seconds. There is also a second relationship that exists, and that is between the wavelength of a wave of electromagnetic radiation and its frequency. And they are, if you multiply the two together, you should always get the same constant, and that constant is the speed of light. And the speed of light is a constant in a vacuum, and it can change a little bit if you put it in different substances. Light traveling through water travels a little slower, but for the most part, this is an appropriate approximation for the speed of light going through air, and that represents the details of the experiments that we typically conduct in a laboratory. And so it's kind of the same deal where we can, if the question asks us for a wavelength of the photon that we had originally, and I already determined its frequency, then wavelength is the variable that I want to solve for. So I'm going to take this equation where C is equal to wavelength times frequency, divide both sides by frequency to rearrange it algebraically, and now I have it set up that the wavelength is equal to speed of light divided by the frequency. And so the speed of light is 3.00 times 10 to the 8th meters per second. When I divide that by the frequency that I calculated up here in question 1, I end up with 4.00 times 10 to the negative 7th meters. So this was the original answer that I got from this equation. But then it's common for us to not want to deal with large or very small exponents like 10 to the negative 7th. So we use our different metric prefixes, and I'm going to switch this over from meters to nanometers by multiplying by the relationship between nanometers and meters. 1 meter is equal to 10 to the 9th nanometers, and so I can multiply that conversion factor by my value, and I end up with 400 nanometers. The reason that I wanted this in nanometers was so that I could then look at a typical electromagnetic radiation spectrum. Spectrum is a better term for this, and I know that because I just Google searched it. So here is a typical visible light, electromagnetic radiation spectrum. And this refers to all different types of electromagnetic radiation and orders them based on their wavelength. And so you'll notice hopefully again this is familiar to you, but X-rays and gamma rays tend to have very, very, very short wavelengths, which would result in them having very high frequencies, which also results in them having very high energies. And that's why, biologically speaking, X-rays and gamma rays tend to be more destructive. visible light spectrum, which happens to correspond to those specific photons that we have hardware in our eyes to interact with. So visible light is really not different from a physical perspective than radio waves or infrared light. It's just of a specific wavelength. But biologically speaking, it's special to us because we have very special receptors that pick up visible light. And it's usually between about 450 nanometers and 700 nanometers is what our eyeballs can detect. And this is a pretty generous visible spectrum right here. And so that photon that we have been talking about in the questions so far in the lesson was at 400 nanometers. And that corresponds to right on the boundary between visible light in the purple area and ultraviolet light down here. Sorry, violet. This is violet. So the photon that we looked at was violet / ultraviolet. Right on that boundary is where it sits. Looking at a second example, we're going to compare two photons. Photon A has a wavelength of 435 nanometers and photon B has a wavelength of 555 nanometers. What color is each photon? So A is going to equal some value, some color, and B will be some color. Let's go back to our spectrum. 435 nanometers, so these are in increments of 20, 420, 440, 460, 485. So right there, that's going to be blue-violet, we'll call that. And 455 nanometers would be right here, and we'll say that's green. It's right on whatever this boundary is. Is that chartreuse? We'll just call it green, and this one over here is blue to make our lives simpler. So A is blue, and B is green. Which photon has a higher frequency? And so these second two questions right here. So the first question, its purpose was to help you understand that a specific wavelength value allows you to find a home for it on this diagram. So once you know the value, you can like pin the tail on the donkey. You can put that photon right where it belongs. The second part of the question is to help you see that there is a relationship between wavelength and frequency. Because whenever you multiply the two together, you have to get the same value. That means if wavelength goes up, in order to get this still the same value, frequency has to come down. They are referred to as inversely related. So which photon has a higher frequency? Well, higher frequency corresponds to shorter wavelength. Therefore, the shorter wavelength is photon A has a higher frequency. And this is an important relationship, and you should be able to kind of bounce back and forth in these in your mind. So if you see, going back to this diagram, that this corresponds to things with shorter and shorter wavelengths, and therefore corresponds to things with higher and higher frequencies. Finally, the relationship now between energy and either frequency or wavelength. Based on Planck's equation, energy is equal to some constant times frequency. Because the constant stays the same, if you raise the frequency and then multiply it by a constant, that will raise your energy. These two are directly proportional, meaning that a higher frequency corresponds to a higher energy. Or we could say that a shorter wavelength also corresponds to a higher energy. Wavelength and frequency are opposite of each other. They're inversely related. Frequency and energy are directly related to each other, and therefore wavelength and energy are inversely related to each other. We already said that photon A is a higher frequency, and therefore photon A will have a higher energy. Now, the nature of a sunburn is a physiological process, but the energy associated with the photons that cause a sunburn is meaningful. And if you're aware of the science of sunburns, you'll hopefully be aware that ultraviolet light is typically the photons that are blamed for sunburns, and rightfully so. And along the spectrum, now our sun, the star closest to us, happens to give off light that pretty directly matches the visible spectrum. So the most common photon given off by our sun is right in the middle of the visible spectrum. And that makes sense. As humans, we would expect to evolve to take advantage of the peak photons coming off of the sun. And the sun does give off it gives off mostly light in the visible spectrum, but it also gives off quite a bit of light on the sides. So ultraviolet light comes off the sun and infrared light comes off the sun. The ultraviolet light is what causes sunburns, and those happen to be among the highest energy photons that are given off in large abundance by our sun. A good chunk of that ultraviolet light is supposed to be filtered out by the ozone layer in the upper atmosphere, but still quite a bit makes through, and that's why it's a good idea to apply sunscreen. Infrared light is interesting in that we don't have sensors in our eyes to detect it, but infrared light, as we saw, as you hopefully remember from the discussion of infrared spectroscopy, causes molecules to start to vibrate. And you can detect that increased vibration as a heat sensation. So when you kind of bask in the light of the sun and it makes you feel warm, one of the things that's going on there is the infrared light from the sun is starting your molecules vibrating, and you're noting that they are increasing their vibrational energy state by increasing their temperature. So your nerves will actually sense infrared light indirectly by determining that your skin temperature is going up. So we do have essentially IR detectors, and if you are in a dark space that you can't see anything with your eyes and you hold your hands out and feel for a heat source, you are essentially trying to see in the infrared spectrum with your hands. Okay, just to pound this concept home, we want to get this relationship down again. As the wavelength of a photon increases, the frequency will decrease because they are inversely related, and the energy does whatever the frequency does. So if the frequency decreases, then the energy will decrease. That is because wavelength and energy are inversely proportional. As one goes up, the other goes down. And frequency and energy are directly proportional. So there we have identified the relationships as clearly as possible. All right, the next concept to think about is what happens when individual photons interact with matter. So here is a Bohr model of hydrogen. This is definitely an oversimplified view of what's going on in a hydrogen, but it is a model that works for this particular explanation. Here's the nucleus of a hydrogen atom, and here's the electron. And if we apply the Bohr model across the board, you can just kind of pretend that this generically denotes any atom, and it has a nucleus with electrons surrounding it. A photon is often shown as a particle with a squiggly line. This intends to show the wave-particle duality of light. And so that's kind of a clever little historical reference of the argument between waves and particles. So the photon comes in and it runs into that electron. And if the photon has exactly the right amount of energy, it will cause the electron to hop from a lower energy state to a higher energy state. And after a very short amount of time, that electron will drop back down again and release that energy in the form of a new photon. So this is the absorption of energy, and this is the emission of energy. And if this process operates perfectly, then the photon that is given off is exactly the same type of photon that comes in, but entropy always exacts some toll. Now let's try to summarize our thinking on this one. So based on the diagram above, what we should have realized was that the lowest energy state for the electron right here is referred to as the ground state. When an atom absorbs energy, the electrons move from the ground state to the excited state. So the second one is absorbed. That's what's happening. The photon comes in, the electrons, or the atom itself actually absorbs the energy into the electrons, and they pop up to a higher energy state. And then the atoms will release energy when the electrons drop from a high energy state back down to their ground state again. So these principles are exploited in spectrophotometry by using some type of electromagnetic radiation source. So in today's lesson, it would be a source of ultraviolet radiation. with some visible light usually playing a role there as well. So you have a source of radiation, then that fires those photons at your chemical sample. The chemical sample will absorb some amount of radiation by transitioning the electrons from the ground state to an excited state, and then the resulting radiation that makes it through to the detector is missing those wavelengths of light that were absorbed by the chemical sample. I remember the first time that I saw this and I thought, wait, doesn't the chemical sample just give those photons back? And therefore, wouldn't the light coming through to the detector have all of the photons back again? And the answer is yes and no. So the issue here is directionality. Typically, you fire the electron magnetic radiation at this chemical sample. It absorbs specific wavelengths of light that correspond to these electronic transitions. But then when it fires these wavelengths back out again, it does them in scattered direction. So the probability that it will send them to the detector is very low. So this is a directional light source. The chemical sample scatters some of the light that specifically corresponds to the frequencies of light that it will absorb, and then the rest of the light makes it through to the detector. Okay, so let's think about what a hydrogen atom would do inside of this type of setup. So we have an electromagnetic radiation source. It fires photons towards your chemical sample. The chemical sample is going to absorb some of those wavelengths, and then the resulting light will make it through to the detector without those waves of light that were absorbed by your chemical sample. Hydrogen specifically absorbs waves of light that have a wavelength of 102.6 nanometers. And so what the detector will read is if you set up the experiment so that you're recording any waves from 100 nanometers to 120 nanometers, and those waves of light are making it through to the detector, we refer to that as 100% transmittance. And then where the sample absorbs some wavelength of light, less of that photon will make it through to the detector, so the transmittance will be some value less than 100%. Sometimes they'll just invert this, divided by 1, or sorry, 1 divided by that value, basically, and you end up with, along that same spectrum, instead of looking at transmittance, where most of the light is making through to the detector, you look at absorbance. Absorbance looks at life from the perspective of the chemical sample. Transmittance looks at life from the perspective of the detector. And you'll see both of these types of spectra. And the key is that they both tell you that something unique is happening at exactly 102.6 nanometers. Organic chemists are less interested in hydrogen and more interested in organic molecules. And UV Vis spectroscopy specifically looks at the conjugated pi systems of organic compounds. In order to understand how photons interact with these conjugated pi systems, we need to look at the molecular orbital diagrams of just the pi systems. And fortunately, hopefully, the idea of these molecular orbital diagrams is already one that you've kind of grappled with when we discussed Diels-Alder chemistry. So looking specifically at 1,3-butadiene right here, its pi system can be described using these frontier molecular orbital diagrams. 1,3-butadiene has 4 sp2 hybridized carbons. Each of those sp2 hybridized carbons has an unhybridized p orbital that is directly involved in the conjugated pi system. If you have 4 atomic orbitals, then you should generate 4 molecular orbitals. So we have this 4x4 grid where the bottom 2 orbitals are net bonding and the top 2 orbitals are anti-bonding. Once you've diagrammed out your 4 molecular orbitals, then you can put up to 2 electrons in each orbital. 1,3-butadiene has a total of 4 pi electrons, so 2 of them will go in this lowest energy orbital, and 2 of them will go in this slightly higher energy orbital. Now we've got a full molecular orbital diagram that describes the conjugated pi system of 1,3-butadiene. We can label these orbitals. The lowest energy occupied molecular orbital is this one here on the bottom. The highest energy occupied molecular orbital is this one right here. And the lowest energy unoccupied molecular orbital is one step up. And finally, the highest energy unoccupied molecular orbital. I've never heard anybody care about the LOMO or the HUMO. It is always the HOMO and the LUMO that matter when we discuss chemical reactions. And for UV Vis spectroscopy, it is this relationship between the energy of the HOMO and the energy of the LUMO that we are specifically probing with our spectroscopy. So this is what happens when you shine UV light on 1,3-butadiene. That UV light represents an energy source. The molecule absorbs the energy by promoting one of its electrons to a higher energy state. So this is the ground state, the lowest energy state of 1,3-butadiene. And here, this represents an excited state, where one of the electrons in the HOMO gets promoted to the LUMO. And the energy is stored in this electron now. This is what UV light does. And if we set 1,3-butadiene inside of our detector, so here we put it, we have a chemical sample right here. We put 1,3-butadiene in there. We shine ultraviolet light on there. And the energy associated with that HOMO-LUMO transition, that photon will be absorbed by the chemical sample, and the detector will identify that some photons have not made it through to the detector. So just like hydrogen produces a peak in this transmittance diagram, or a peak in the absorption diagram, we're going to see a similar peak when we shine UV light on these conjugated pi systems. And the peak will tell us the wavelength of light that is required for a HOMO-LUMO transition. And that particular peak represents a fingerprint that gives us an indication as to the structure of the compound. Most UV Vis spectroscopy focuses on absorption, and the absorption bands are kind of messy. So isoprene right here is a common molecule that we use as organic chemists. It's kind of a neat little building block. It is conjugated in a very similar fashion to 1,3-butadiene. So it's got two pi bonds, so it would have the exact same energy diagrams as 1,3-butadiene. And when you shine UV light on isoprene, it at a maximum of 222 nanometers, that's where the most probable removal of UV light occurs. And that's because those are the photons that are causing one of these 4 pi electrons to be promoted from the HOMO to the LUMO. And the energy associated with a photon of 222 nanometers right here is the energy difference between the HOMO and the LUMO diagrams. One of the cool things about UV Vis spectroscopy is while isoprene and 1,3-butadiene only differ because of the presence of this methyl group, it actually results in a slight difference in this lambda max. This lambda max is the most likely photon that gets removed during that HOMO-LUMO transition. For isoprene, it occurs at 222 nanometers. For 1,3-butadiene, it occurs at 217 nanometers. And so when that peak moves to a different position, it gives you an indication as to what that particular molecule is. And 1,3-butadiene is pretty unique. It's one of the few molecules that will produce a peak at 217 nanometers. Isoprene, there's other molecules that will also produce peaks at 222 nanometers. But if you have an unknown sample and you put it in a UV Vis detector, you could distinguish between whether that unknown sample was most likely to be 1,3-butadiene or isoprene based on the wavelength of light that gets absorbed. It's 217 for 1,3-butadiene and 222 for isoprene. This is the usefulness of UV Vis spectroscopy in identifying organic compounds. So this is typically referred to as a pi to pi star transition, or the bonding to the anti-bonding transition from the HOMO, which is the bonding orbital, to the LUMO, which is the anti-bonding orbital. But you could also think of other transitions that could exist. For example, you could transition from the LOMO to the LUMO, or from the LOMO all the way up to the HUMO, or you could also transition from the HOMO to the HUMO. I'll show you what those look like because those words sound like I'm speaking gibberish. So this transition from the HOMO to the LUMO is the most common. You could imagine also the LUMO, sorry, this is the LOMO. Remember the made-up words that I came up with? We could promote one of these LOMO electrons up to the LUMO. You could also move one of the HOMOs up to the HUMO, or the LOMO all the way up to the HUMO. Those are different possible transitions. But again, the most probable transition is simply the HOMO to LUMO transition. And that's why you see this peak right here. That is your HOMO-LUMO transition. These kind of side peaks right here represent the various other options that exist, and they do cause this to be quite a wide band, is typically what this is called. But if we just kind of narrow in and focus directly on the kind of the highest peak right there, that's what we're going to look at from here on out, for the sake of simplicity. Now for the next examples, I need to move to longer conjugated systems. So instead of a 4x4 grid, we need to come up with the idea of a 6x6 grid or an 8x8 grid. But rather than go through and show all of these diagrams, I'm just going to strip it down and look only at these lines right here. And so if you have a 6x6 grid, then you're going to have 6 of these lines and 3 of them will be filled. If you have an 8x8 grid, then you'll have 8 of these lines and always half of them will be filled with electrons. So that's why these diagrams right here represent a much simpler view. 1,3-butadiene can be thought of having 4 molecular orbitals. This would be the HOMO and the LUMO. E135-hexatriene has 6 total carbons, and so it would be a 6x6 grid. But all we're going to look at here are just these energy levels, and 3E5E1357 octatetraene is going to have 8 total orbital diagrams right here. Okay? So this allows us, in more simplicity, to just focus on what are the different energy levels, and notice how in all cases the bottom half of those energy levels are the ones that are occupied. When I shine UV light on 1,3-butadiene, the most probable occurrence was that a photon of 217 nanometers struck the molecule and popped one of the HOMO electrons up to the LUMO. When I shine UV light on this molecule right here, the most probable event is that at some wavelength, a photon will cause one of the HOMO electrons to pop up to one of the LUMO electrons, and for this third compound, at some wavelength, a photon will cause the HOMO-LUMO transition that we've seen over and over again. The important thing is that that wavelength changes depending on which of these 3 molecules that it is. So if you have 3 unknown samples, and you know that one of them is 1,3-butadiene, and one of them is this compound, and one of them, we'll call this compound A, B, and C, but you don't know which of the 3 compounds it is, you can set each of those compounds separately in the UV Vis detector, and it will give you 3 different values. And then it's just an issue of matching up each value with the correct compound. Figuring out how to match each value with the correct compound is where that's what we need to learn next. And the diagram kind of gives us a clue. 1,3-butadiene is intentionally shown with the largest gap between the energy level of the HOMO and the energy level of the LUMO. And this compound, compound C, 3E5E1357 octatetraene, has the smallest gap between the HOMO and the LUMO. And that's on purpose, because as your conjugated system gets longer and longer, the energetic gap between the HOMO and the LUMO starts to narrow. And if it takes less energy to promote an electron from the HOMO to the LUMO, then that means that it will take a different wavelength of light to cause that transition to occur. Now, reaching back into the earlier ideas from this same lesson, a smaller amount of energy corresponds to a longer wavelength. So the largest gap corresponds to the largest energy transition and the shortest wavelength. The smallest gap corresponds to the smallest energy transition and the longest wavelength. So which of these molecules would require the lowest energy photon to effectuate a transition of a single electron from the HOMO to the LUMO? Well, a larger conjugated system requires less energy. So it would be this 3E5E, whoops, this is going to take me a while to type, 5e 1, 3, 5, 7 octatetraene. And so this one would require the lowest energy. And explain. Okay? Well, a larger conjugated system has a tighter energetic spacing between the molecular orbitals. And therefore, less energy is required to move electrons one step up from the HOMO to the LUMO. So now let's think about this. We have a mixture of the three compounds. So we just put all three of them inside of the same container. And what our diagram would look like is, now that we have three different compounds in there, you're going to have three different max values. Right? And they'll come up at different. You'll see these three different maximums. It says that one of the maximums was at 217 nanometers, one was at 253, and one was at 289. Well, based on the answer to question number 9 here, a larger conjugated system has a tighter energy spacing, and therefore less energy is required. If less energy is required, that corresponds to a longer wavelength. And so I'm just going to copy these words right here, and we'll paste them right there. And so of the three compounds that we have right now, this 1,3-butadiene is going to have the largest energy gap and therefore the smallest wavelength. The largest conjugated system will have the smallest energy gap and therefore the longest wavelength. And the middle child just gets whatever's left over. Okay. So again, the more and more that you conjugate your system, the longer the conjugated system tends to be, the longer that wavelength is going to be. Now, you may not have taken the laboratory in the semester that you're listening to this video, but in the laboratory, we actually use an ultraviolet lamp to visualize spots of compounds. And so what you do is you have these unknown compounds and you shine a light on them. And when the compounds are on the substance that we're shining the light on, we see a black spot. And the black spot means that the black spot occurs because the conjugated pi system in that particular compound is absorbing light, is absorbing the UV, and it's actually the visible light at that point because you're seeing it with your eyes. And so what we were really doing in the laboratory was looking for evidence of a conjugated pi system. If you've worked in a biochemistry or a molecular biology laboratory, proteins and DNA have conjugated pi systems. And the conjugated pi system has a specific absorbance at a given wavelength. And you actually set up a detector when you're trying to identify the presence of DNA to look for that particular wavelength. The point is that UV Vis spectroscopy does get used quite a bit in very simple ways in order for us to identify the presence of a conjugated pi system. Let's go back a minute and think about the two examples that we saw before, and that is 1,3-butadiene and isoprene. 1,3-butadiene has a lambda max of 217 nanometers, but isoprene has a lambda max of 222 nanometers. And as a chemist, it would be perfectly reasonable to notice that the only difference between 1,3-butadiene and isoprene is the presence of an additional methyl group on isoprene. And you would reasonably then ask, is a methyl group, does it predictably cause the lambda max to go up by 5 nanometers? What if I put a second methyl group on there? Would it go up by another 5 nanometers? And what if it was an ethyl group instead of a methyl group? And all those questions were ones that two chemists named Fieser and Woodward eventually looked at enough data to start to come up with some predictable patterns. And these Fieser and Woodward rules are powerful because they allow you to evaluate a conjugated pi system based on these 6 numbers and their definitions that you are going to need to memorize and come up with an estimate for what that lambda max is most likely to be. First, we need to think about the 3 different types of base values. They are free dienes, S-cis dienes, and S-trans-dienes. So let's look at this example of 2,3-dimethyl-1,3-butadiene. So I took a 1,3-butadiene and I just tacked 2 methyl groups on it. Now, the 1,3-butadiene is free to rotate along this single bond. So some of the time it will be in an S-cis conformation, and some of the time it will be in an S-trans conformation. Contrast that with this example right here. So this would be 1,3-cyclohexadiene, and these 2 pi bonds right here are currently in an S-cis fashion, and they are locked in an S-cis fashion. They can't rotate out of that. The ring system prevents the rotation. So the base value for this S-cis system that's locked in that conformation is 253 nanometers, but the base value for a diene that's free to undergo rotation is 217 nanometers. And that's all there is to 1,3-butadiene. It is just a free diene with no methyl groups. So if these were hydrogens, this would be 1,3-butadiene. And we saw earlier that its lambda max was 217 nanometers. When we tack on a single methyl group for isoprene, the lambda max went from the base value of 217 up by 5, and that is predictably what we see. Anytime you add an alkyl substituent to a free diene, whether it's a methyl, an ethyl, a propyl, whatever, you're going to see that that lambda max value will go up by 5. Where we put 2 methyl groups on there, then we would expect it to go up by 5 twice. So the Feser-Woodward rules would tell us that the base value for 2,3-dimethyl-1,3-butadiene is 217 nanometers because this is a free diene, plus 5 for this alkyl group and 5 more for this alkyl group. And the reason that you add 5 is not because of what's out here on the end, it's because of the presence of this bond. And that will matter more in a second. So the best way to describe this is any single bond that comes off of your conjugated system is going to add 5 nanometers to your lambda calc, the calculated lambda max value. Lambda observed is what you actually experimentally derive in the laboratory, and we find that it's 226 nanometers, whereas the Feser-Woodward rules expected it to be 227 nanometers. And that's good. Like, that's good enough. If you are plus or minus 5 nanometers, then the Feser-Woodward rules have done what they were supposed to do. So 2,3-dimethyl-1,3-butadiene has a lambda calculated of 227 nanometers, which is actually quite close to the 226 value that you observe in the laboratory. So we're going to use these Feser-Woodward rules until you've kind of understood how to apply them to various problems. It will be on you to memorize these values and then learn how to apply them, but I'm going to show you several examples where we can apply these repeatedly so that you get a good feel for how they work. Before we look at more examples, let's think about, what does 5 nanometers mean? How much energy difference is that? Well, going back to these 3 diagrams right here, what we saw was that for a smaller conjugated system, there was a larger energy gap between the HOMO and the LUMO. A larger energy gap corresponds to a shorter wavelength. So when you add 5 nanometers, that's increasing the wavelength, and because they're inversely proportional, decreasing the energy. So the effect of adding in extra methyl groups will actually shrink the gap between the HOMO and the LUMO. By shrinking the gap between the HOMO and the LUMO, you're actually bringing the HOMO to a higher energy state, which destabilizes the bond. So technically speaking, adding in methyl groups actually disrupts your conjugated system. That reduces the difference between a bonding and anti-bonding conjugated system. If it's weaker, there's less difference between bonding and anti-bonding. And so the energy gap between HOMO and LUMO is smaller, and therefore the wavelength is longer. That's why we add in that 5 nanometers. How much is 5 nanometers? Well, we can the energy of a photon is equal to Planck's constant times the frequency, and the wavelength, which I'm just going to abbreviate as W just so I don't have to find the symbol font, times the frequency is equal to the speed of light. Wants to capitalize that. So I'll just W, that's the wavelength, WV. I'll refer to that as wavelength times the frequency is equal to the speed of light. Well, if we solve this one for frequency, frequency is equal to the speed of light divided by your wavelength. Oops. Then we can substitute F into this equation right here. Okay? So I'm going to say E is equal to H, and now instead of typing F, I'm going to type C divided by wavelength. So this is actually me combining those two equations into a single, better equation, kind of like Megadesk. But the wavelength now needs to be in units of meters. Well, 5 nanometers is actually 5 times 10 to the negative 9th meters. And the Planck's constant is 6.63 times 10 to the negative 34 joules seconds. And that's not a value that you have to memorize. You probably did at some point, and if you already forgot it, then clearly it wasn't that important. So, and then speed of light, which you probably should know as well, but I won't expect you to memorize that because you've got other stuff that's important for me to have you memorize, times 10 to the 8th meters per second. Okay, so now we've got everything set up, and this will allow us to calculate the energy difference. So I'm going to plug these into a calculator and spit out some value. All right, the magic of calculators told me that the value was 3.98 times 10 to the negative 17th, and I assigned it a negative value because if I'm increasing the wavelength, that means the energy is going down by that much. So every alkyl group that you tack into your conjugated system is going to reduce the energy of the HOMO-LUMO transition by 3.98 times 10 to the negative 17th joules. Let's now consider an example and come up with a lambda calc value by applying the Woodward-Fieser rules. So we're going to look at 2,5-dimethyl 2,4-hexadiene. And I already drew that one and looked at the calculations. Spoiler alert, there's the answer. But here's this compound. Whoops, 2,5-dimethyl 2,4-hexadiene. This is a free diene. It is free to undergo rotation. The only time that you're going to see not free dienes is typically when there's some type of ring in the system that prevents rotation of that bond. So free dienes start with a base value of 217 nanometer. And then once I've established that this is the conjugated system, I look for any single bonds coming off that conjugated system that are not part of the conjugated system. So this is also a single bond, but it's connecting the conjugated system together. So that's already accounted for in the 217. So these 4 single bonds each will add in 5 nanometers. So if I want to be more explicit about this, then this is the base value. And it's the base value for a free diene. And then we add in plus 4 times 5 nanometers because of the 4 alkyl bonds. And so this gives us a total of 217 plus 20, or 237 nanometers right there. That's our final answer. The Fieser-Woodward rules for determining lambda calc are usually accurate to plus or minus 4 nanometers. So if lambda observed for this compound is 241 nanometers, does your answer fall within the Fieser-Woodward limit for error? Then yeah, because this is within 4 nanometers. Our lambda calc is within 4 nanometers of lambda observed, so yes. And it doesn't ask us to explain it, but for the sake of our own notes, we should. 237 and 241 are within 4 of each other. Scientists, we should definitely put units on these, so 4 nanometers of each other. So that definitely means that I made a mistake earlier when I said that it was plus or minus 5. I didn't even read my own writing there that this 5 had nothing to do with the margin of error. Instead, it's plus or minus 4. So your Feser-Woodward should give you plus or minus 4 of the actual observed value. So here's an example of cyclohexadiene. This is a ring system that locks it in a permanently S-cis conformation. So the base value for S-cis is 253 nanometers, and then there are these two lines that are coming off of the conjugated system that are not part of the conjugated system. So we add in 2 more units of 5. So the lambda calc for this compound right here, cyclohexadiene, should be 263 total. 253 from the base value, and then 2 more because of the extending alkyl groups right there. Determine lambda calc of 2,3-dimethyl cyclohexadiene. So 2,3-dimethyl cyclohexadiene is this same cyclohexadiene right there, but it has 2 additional methyl groups. They would show up coming off of this position and that position right there. So let's draw a structure of that compound. It would look like this, and we have the 2 methyl groups coming off of it. So we're going to apply kind of our same type of calculation that we looked at before, where the base value is going to be 253 because it is locked in a permanently S-cis fashion for an S-cis. And then we're also extending 4 alkyl bonds. So these 4 carbons right here define the conjugated system, and across all 4 of those carbons there are 1, 2, 3, 4 bonds coming off. So it's going to be still that same add of 4 times 5. So we're going to take the 253 and we're going to add 4 times 5 to it, which is 253 plus 20, or 273 nanometers. All right, let's look at another example. This is cholesta 2,4-diene or 2,4-cholestadiene. And you might notice some similarities to the word cholesterol, and there are some structural similarities between this and cholesterol. The diene within this system right here is an S-cis diene. It is permanently locked by the ring system so that the pi bonds are always going to be in the S-cis orientation. So this is an S-cis diene, and that would give us a base value of 253, and then it asks us to identify alkyl groups connected to the conjugated system. So off of this conjugated diene right there, there is a line that extends down to the right, that's 1, a line that extends up, that's 2, and then this line right here that extends over and up to the right. So there are 3 different alkyl groups coming off of this, and it asks us to identify them. So I'm going to make a note of where those are. And so I'll just use this line right here to mark where those alkyl. There's 1 alkyl group, there's my 2nd alkyl group, and there's my 3rd alkyl group right there. Okay, so now we've kind of got the bits and pieces. If you have an S-cis, then we expect it to be 253 nanometers. And then for each of these 3 alkyl groups, that adds in 15 more nanometers. But now we need to introduce the last component of the Feser-Woodward rules. If you go back up to the table, this is that exocyclic double bond. And this tends to be, I think, fairly confusing for students. And so maybe I don't explain it well, but this is the best explanation I can offer you. An exocyclic double bond is a double bond that starts as part of a carbon in a ring system and does not end within that same ring system. So notice how this double bond starts on that carbon. And that carbon can be assigned to this 6-membered ring, but the double bond does not end anywhere inside of that 6-membered ring. And so that makes this an exocyclic double bond. And you might ask, well, wait, but it does start and end within this 6-membered ring, and that's true. This pi bond is on that carbon, which is part of this 6-membered ring, and it ends on that carbon, which is still part of that same 6-membered ring. So it's not exocyclic relative to this ring, but it is exocyclic relative to that ring. And the reason that the exocyclic pi bond is a problem and changes your energy is because it actually inhibits the proper chair conformation of this six-membered ring right here. So it's an energetic penalty, and it costs it 5 nanometers. So what is the lambda calc for this molecule? Well, what we came up with was the base value is 253 nanometers plus 3 alkyl groups at 5 nanometers apiece plus 1 exocyclic bond at 5 nanometers. And so this is equal to 200, and we're going to add 20 to this, so 273 nanometers. That's what lambda calc is. Lambda calc. And this is within the 4 nanometers that we're supposed to observe based on the Feser-Woodward rules. The next example finally gives us an S-trans conformation. So notice how these two pi bonds across that single bond are locked in trans arrangement. And because of the ring structure, they really are not free to undergo a rotation. So this one has a base value of 214. So that's my base, 214 nanometers plus. And it says that the lambda calc for this molecule is 234. So we're going to add 20 more nanometers. Well, let's find out where those are coming from. First, we'll look for the alkyl groups. Off of the conjugated diene, I see 1, 2, 3 lines right there. So that means we add in 3 times 5 nanometers. And this is for the alkyl extensions. And we're missing 5 nanometers, so the only other thing that can come from is the exocyclic. And let's find that exocyclic. And it is not this pi bond right there. Notice how both of the carbons of this pi bond are part of the same 6-membered ring. And it doesn't have to be 6-membered, just they're part of the same ring. This pi bond right here, both of those carbons are part of this ring. So based on this ring, it does not look exocyclic. But based on this ring, it is exocyclic. An exocyclic pi bond will start on one ring and extend out of that ring, which is what's going on right here. So that's where the exocyclic is coming from. At this point, we've kind of explored the very simplest aspects of the Feser-Woodward rules. If you start getting very creative, then this table that I showed you right here starts to expand. In fact, the table that I saw in my graduate course was covered 2 full pages, and there's just all kinds of little additions that they have to add in. So I'm just taking a very small snippet of that so that to give you a taste of how you can use a few simple rules to predict the lambda max or be able to predict what's going to happen in the laboratory, which is always cool to do. It's always nice when you can anticipate how an experiment will turn out, and then it actually turns out that way. So let's look at this compound right here and talk about the lambda calc. And I've given you the answer that is 303 nanometers. Let's come up with justification for that answer. But we need to kind of read this line up here. You may have to choose between 2 different base values. Always choose the base value of the longest lambda calc. And this compound illustrates that. This is an S-cis diene. But this overall is a triene, which means that there's going to be a diene on this side and a second diene right here. And if you choose this as your base value, you'll start off at 253. If you choose this S-trans diene as your base value, then you start off at 214, and you always choose the higher of the 2 values. So my base value is 253 nanometers because there is an S-cis somewhere within the conjugated system. Okay? Now, I'm going to add in 30 nanometers because it is a triene. If it was a tetraene, you would add in 2 times 30, etc. That was the one more kind of row on the Feser-Woodward rules that we needed to look at, was each double bond that extends the conjugation tacks 30 more onto the diene value. So we've got a third double bond right there, so that's going to give it 30 nanometers. Now we need to start adding in well, we can do exocyclic, but we've been doing those last, so I'll save that one. So we're going to have some number right here of alkyl groups that extend off the conjugated system. So let me make a note of those ones right here. There is, off of this large conjugated system, that is an alkyl group that comes off of it. that is an alkyl group, and that right there is my third alkyl group. So that means that I have 3 different alkyl groups that are breaking off of that conjugated system. And now I need to see if there are any exocyclic ones. So that's the last thing we check. Each exocyclic will add 5 nanometers. And hopefully you're getting good enough at these that you can already see that this is the pi bond that's exocyclic right there. So I have one of those that's exocyclic. And I'm going to make a note of this exocyclic, and I would encourage you to do the same, just so that you're aware of what your answers mean when you go to study for the exam. Alkyl group. Okay, so now we just do the math. Add all these together, and at this point, hopefully we get 303. So 253 plus 30 is 283. Plus 3 times 5 is 298. Plus 5 more is 303. So that's where we get all of this from. I will go ahead and allow you to work on the last 4 on your own. This is not material that your textbook talks about. The Feser-Woodward rules are not something found in your textbook, but I think it does a couple of things that are helpful. First of all, it shows you that with all the forms of spectroscopy, you're going to need to focus on some memorized tables and then apply those constantly. Secondly, it's a nice overview, it's a nice review of frontier molecular orbital theory. And third is it starts to help you see how we get from data to structure. So you're going to go ahead and apply the Feser-Woodward rules. Just a couple things to point out to be wary of. In letter B right here, there are a total of 1, 2, 3, 4 pi bonds, but they're not all conjugated with each other. Conjugation means that they are connected by a continuous row of sp2 hybridized carbons. And letter D has the same issue. There's a lot of pi bonds in here, but not all of them are fully conjugated with the pi system, and so they don't affect the lambda calc. So be on the lookout for those. Post your answers on the discussion board, and hopefully you learn quite a bit more in doing these practice problems.